It gives me great pleasure to start this afternoon session by introducing our first plenary speaker, Professor Guangming Xie. He's a full professor in dynamics and control with the College of Engineering at Peking University. And if my research did me right, he's also the vice director of the Innovative Thinking Education Center of Beijing University. So he runs the Intelligent Controlled Lab. His PhD degree was in control theory and control engineering from Tsinghua University, with a focus on complex system dynamics and control, robot intelligence. I think all of us know him best for all of his underwater robots, which are super impressive. These robots are actually out there in the real world functioning. He's also the founder of the International Underwater Robotics Competition. And naturally, he's won prizes both in the Chinese National Science Awards and the first prize of the Natural Science of Ministry of Education. So no doubt there's a really exciting talk coming up. And I won't take more of your time. Please take it away, Professor Xie. Can you share your screen?
Thank you. Thank you for your introduction. And also thank you for Professor Ida for his invitation. And good afternoon, everyone. Now I will share my slides. Yeah, can you see it?
We can see the PowerPoint presentation. Yeah, if this is perfect. Yep, thank you.
Okay. Okay. I'm very glad here to have the opportunity to report our work on bio-inspired underwater robots. Yeah. First of all, let me give a brief introduction of my group. Yeah. As one of China's most famous universities, Peking University has a long history. But the College of Engineering is just rebuilt in 2005. Yeah, and we located in the Department of Advanced Manufacturing and Robotics. It's just built 3 years ago. Here is a picture of a golden Arona robot from our lab. Okay, and the Department of Advanced Manufacturing and Robots is the youngest department in our college. Okay. And here is the website of my lab. Though the department is very young, but our research on robotics has been over 20 years. Yeah. My lab's name has 3 keywords. The first is intelligent. Yeah, just like this conference, we think that intelligence represents research prospection. As robot or machine become more intelligent, there's a long way to go. The second keyword is biomimetic. Yeah, we think it represents research paradigm. We believe nature is always a good teacher. We can learn from it persistently and never out of date. The last one is the design. We hope our research results will be applied in real world someday. It needs industrial design and the commercial design process and so on. So scientific research, innovation, and the real world application are both what we expect. And in Chinese, they said as it's here, 顶天立地. Yeah, that means we want our research to touch the sky, the edge of the research. And the second, our research can step on the ground and solve some real problem. Okay. And my lab mainly focuses on the research of underwater robots and underwater unmanned systems. Compared to the land environment, the underwater environment is more hostile and complex. And this development of the water robots faces many challenges. For example, see these two videos. Underwater perception is very weak, and the environment information cannot be obtained easily. And underwater wireless communication is a bottleneck, make it difficult for robots to interact with other robots or systems. There is no underwater positioning system similar to GPS, which cannot achieve precise positioning underwater. And also the dynamic changes in water flow have a significant impact on robot motion. And we also know this event, the Malaysian airline flight MH370. Yeah, despite $200 million investigation spanning 8 years, this plane, which held over 200 people, has still never been found. Though some underwater robots are used to search it, but we finally didn't find it. Okay. So we say that there have been some traditional underwater robots. There are two classes, main classes. One is the remote operation vehicle, briefly ROV. It uses a cable from the ship or the land to get the energy or the information. So the robot, for this robot, the intelligence is very few. Okay. The second one is autonomous underwater vehicle, briefly in AUV. But for these two kinds of traditional underwater robots, the main propulsion mode is propeller. So there are some aspects that needed to be improved, such as low energy utilization efficiency, insufficient mobility for robots, and also large interference with the environment, and the robot is not is unfriendly to the environment. Okay. So the bionic robotic fish emerged as times require. People have developed bionic underwater robots to replace traditional ones. The world's earliest robotic fish was born in 1994 at MIT in US. And it is a tuna-like robot, like this picture. After that, various types of robotic fish have been studied and developed. Okay. So next, we'll introduce the work of our team from the following aspects, including motion, perception, communication, catching, school behavior, robot fish mix system, and two recent results of our group. Okay. So the first is the motion bionics. And here we use this example, boxfish. Yeah. This is a paper from Nature 2015. A curious density of reefs, the boxfish flees among the coral, yeah, from coral, turning this way, and that is feeds on small invertebrates. The fish has been used as the bionic model for a automobile company, but it does not seem to be dynamically gifted because its swimming is neither swift nor effortless. So this paper shows that the shape of this fish have a self stability, and also it has has the fins make it have high maneuverability in 3D environment. Okay, so we think that this boxfish is a good teacher. We should learn from it. So we designed such a boxfish robot. Okay, and we use the 3D technology to get the same shape and design a pair of pectoral fin and a tail fin like this. Yes, the two pectoral fin. All the three pain fins are independent. And for saving space, we use such design such as chips and devices. Okay, and then we also based on the CPG, central generator pattern generator framework to design the motion control architecture. And then we can make the boxfish robot has the 3D maneuverability. For example, it can moving forward, turning left or right, and moving backward. Also, it can floating and submerging. And also, with the pectoral fin, it can vertical rolling, horizontal rolling, and some salted. Some are salted. Okay. And also, we say, based on this prototype, one of my students designed a product. This product is for personal entertainment. You can use this. It's named Beking. Its name is called underwater photography robot fish. When you play or some game in the pool or in the sea, you can take this robotic fish to follow you, take pictures for you. Okay. And also, this product won the Las Vegas CES Innovation Award. Okay. It's just based on our boxfish robot. And the sixth topic is perception bionics. Okay. And we all know that the traditional underwater perception have two classes. First, acoustic, some of the active sonar or passive sonar. But based on these devices, the information is very limited. And the second is visual, using camera or lidar. But also, when the water is turbid or the light is dim, the information is also not enough for the under environment perception. Okay, but we think that the fish also face the same bad environment. But how does the fish solve this problem? We found that the fish has the littoral line system. It's a unique perception organ for underwater environment. Okay, just like this fish. It consists of flow responsive receptors distributed all over the body, and some of them on the face. Okay, based on this literal line system, the fish can finish very important phenomena for themselves, such as the rotatics behavior. And based on the literal line system, it can find sense the obstacle, find the predator localization, and also find its colleague, make the fish become a group, and also even it can energy harvesting from the vortex street follow the fish. Okay, so it's a very important perception from the fish. So we want that our robotic fish also had such a underwater perception system. So we use the pressure sensor, just use 9 pressure sensors, 3 on the left, 3 on the right, and 3 on the face. Okay, so only we just use the 9 pressure sensors to compose artificial literal line system. Based on this, we can perception some information. The first is that speed self-evaluation for a freely swim robot. Okay, here we use such environment, tank, and use the camera to record the speed of the robot. And then also this robot fish has the artificial literal line system. We can record the pressure. Sorry, this is the record for robotic fish. Different pressure sensor have a different record. And then we based on this pressure sensors, we can evaluate the speed. We can see this picture. The blue line is the real speed computed by the camera from the video, and the red line is evaluate speed from the literal line system integrate of the fish body. Okay, the error is very small. And moreover, we developed the second artificial literal line system. Not only this array of pressure sensors, we use 2 more sensors on the top and the bottom. And then based on these 2 sensors, we can evaluate the motion trajectory of the robotic fish. Here is the main result for this artificial literal line system. We can use the system give online state estimation, including the linear velocity, angular velocity, motion radius, and the trajectory. And the method has these three parts. Corresponding pressure variation model that links motion parameters to PV's surroundings the robotic fish is built. And then a linear regression analysis method is used for determining the model parameters. Finally, motion parameters can be estimated by serving this PV model inversely. Okay, here shows different motion process. Some is in the 2-dimension. The last is in 3-dimension environment. Okay. Here is a video show how the artificial litter line system work. Okay. Yeah, use different motion parameters. The fish can swim in the tank. Then they can evaluate the trajectory of the turning motion like this. This is the gliding motion. It's a spiral motion. Okay. This is, I think, this is the first paper that use this artificial litter line system can give online state estimation of a fish-like robot. Okay. And moreover, we not only estimate the state of the robot fish itself, we can also want it can be it can sensing the neighboring robot. And it means here we have 2 robots. First is the swimming, just a swimming robot. And the second have integrate with the artificial litter line system. And then once the swimming robot moving or swing his tail fin, and then the second fish can collect the data from the artificial litter line system. Okay, just like this. This is a swimming robot and the sensing robot. And just we want to base this data, we can estimate the distance between the 2 robots. Okay. And here is the result. Use different position of the sensor pressure, and we can detect the distance between these 2 robots. Okay, but this very fundamental work. The fish is fixed in the tank, and then the flow is dynamic. And in the future, we will do some research with free swimming robot. Okay. Then this is the perception bionics. The next is communication bionics. Communication, that means we all know communication is one of the most fundamental capabilities for underwater robots in real application. When an individual robot is executing an underwater assignment, the remote control center should monitoring the state of the robot and implement necessary intervention on the robot, if necessary, through underwater communication. In addition, when a group of underwater robots are performing collaborative tasks, such as patrolling seaports, searching and monitoring oil spills, they need to communicate underwater for information relay, motion coordination, and formation control. So the widely used electromagnetic methods not well established for digital communication in the air. For example, the 5G technology is very popular in China now and in the world. It can hardly work, but this electronic magic method can hardly work under the water. Acoustic method is the most commonly used for underwater communication. But it also faces challenges of large Doppler shifts and multipath effect. And also the other method is the optical communication. But this method requires precise alignment between the transmitter and the receiver. Thus, it seems not so practical for the mobile underwater robots. Okay. So how to solve this communication problem for underwater robots? We also from nature get answer. We found there is a class of fish called weakly electric fish. This fish can generate dipole-shaped electrical field to perceive natural electronic stimuli, which is called electric science. Okay. The electric science is used in electrolocation, and for electrocommunication. The working principle is as follows. The senders use a pair of electrodes to actively generate an electric field and send the information in the form of electric field. And then the receiver, here the receiver can extract the information from the electric field generated by the sender. The red is the sender, the green is the receiver. And then electric current communication is built up. Okay, the research can be is from the 1970s. Okay, and then here is the real fish. It's a real big electric fish, and for this we developed a low-cost electrical current communication system and integrate such like this. Here is the first robotic fish, and the second we design circuits and integrate them into our robotic fish like this. Here is the emitter circuit. Here is the receiver circuit. And they think that it's the first time that electric current communication is introduced for underwater robotics. Here's a video show the experiment. Okay, there are two robotic fish. One is the leader, the other is the follower. The leader send command by this electron communication. Just start and swing up over the obstacle. Okay, in the whole process, the leader send command to the followers just by this new underwater communication electro communication technique. Okay, in this experiment, the distance between the two robots can only be 3 meters. It's very short. And now we just want update the system, the hardware system, and the control protocol, the communication protocol to enlarge the distance to 10 or 20 meters. Okay. Moreover, based on this underwater electron communication system, we also can get do the networking task, and we just use the classical CSMA-CA-based electron communication mechanisms on the data link layer to solve the collision problem, and then we develop an ad hoc on-demand distance vector-based routing protocol on the network layer for complex multi-hop underwater electrocommunication networking. Communication is just 2 nodes, but for networking, there may be there's a lot of nodes they need to exchange information. Here's experiment we finish based on this networking technique. Here we have three robots. In the first, we built up the network between them. This fish cannot communicate with this fish, but now they construct the network. Then, then it can send a command from this fish to the second fish and to the third fish. Okay, so that's this shows their communication process. Okay. Okay. The next is a catching bionics. You see, the big fish usually eat small fish. The fish can open its mouth and sucks the small fish into its mouth. Okay. We want to construct such a robotic fish mouth, but it's not easy. Here we just use such a basic result, but it's too large. We cannot integrate into our robotic fish. And so we found that there are any other animals it can catch animals or catch objects more efficient. The dorsal and the ventral membranes. This is an octopus. It has a dorsal and ventral membranes cover most of the arms length of the growing of this animal, and this octopus can use these arms to catch living animals. Okay, by preventing the animals from escaping from the gap between the arms and the increasing the grasping friction phase. Okay. So, inspired by this predation behavior of this octopus, and benefited from the 3D printing and casting technology, our group developed a novel soft gripper with a similar geometrical structure and grasping ability to this octopus. Okay, this is the soft robotic gripper, and the gripper features excellent abilities to suck and grasp objects with any shapes. Here is the grasping behavior in the air. Here is the underwater. And from these two videos, we can show that this gripper can be used to scattering to catch that's the golden fish or the turtle without the fish is also safe. Okay, so this is the our soft robotic gripper. The next is the school behavior bionics, and we have familiar with the fish school. Based on the school behavior, they can let the fish to fight the predators, and also it can increase the probability for foraging. So from the biologist and to the engineering, we want to find what's the basic law for the fish school. Here is the famous model, the cousin model. And since we have robotic fish, we use the same law. That means we use only the local interactions between the fish in this group, and then can produce orderly behavior at the group level. Here is the video show that we use the same law, can show that these three robotic fish can get the same fish school behavior. Okay. It's also called the milling behavior. Okay. And we have remember the MH370 event. I think in the future we may arrange maybe hundreds of or thousands of robotic fish to same way into the under the water to search the airplane. So in that case, we may find the airplane. Okay. The next is the robot fish mix system. It's very interesting. Okay. This picture, it takes that about 10 years ago. We just test the performance of robotic fish, this black one, in our lake, in our campus. But we found that an interesting phenomenon. The robotic fish swim ahead, and then many real fish in the lake follow the robotic fish. Okay. This enlightens us whether we can use robotic fish to control real fish or to influence the real fish. Real fish are more willing to accept this control method, okay, of this control mode. This is a way, we think that this is a way of following the law of nature. Yeah. Here's a potential application. Nowadays, we build up a dam, but we need also with a fishway, okay, just like this. Here is the upstream, the downstream. Here is the fishway or fish ladder. It's necessary because this device is designed to let fish pass around the dam from downstream to the upstream, because the fish need they can continue to the upstream to spawn. Okay, if we have not such a fish ladder, the fish cannot go to the upstream. The fish will perish. Okay, it's a real picture for this fishway or fish ladder. But in fact, the river is too wide. The fish, it's difficult for the fish to find the entrance of the fishway. So we are cooperating with experts in the field of water conservation engineering to study the possibility to using robotic fish to guide the real fish. We teach them to how to control this big one, the robotic fish, and then they buy some real fish from or catch some fish from the river. Then they do some experiment. They show that the real fish, yes, can follow the real fish, the robotic fish for a long time. Okay, here is the record, a radio record for their experiment. Okay, so the fish is our teacher. Now or in the future, we may help our teacher. Okay. And then we have just two result, recent result. The first is that all we know that a deep reinforcement learning is very popular, is very hot for robotics. And we also want to use it for the motion control of robotic fish. First, we just built such a global vision based force estimation and tracking system. And based on use this experiment platform, we can ignore the error from the sensing system. We can get the exact position and the direction or heading for the fish. Let us just focus on the control part. Okay, and then we ignore this. This just we use deep neural network based to get the exact position. And then we design such a general learning framework. We training in simulation and then deploying in the real world. These are 3 steps. The key step is just to build or creating the simulation system. This simulation system has 2 parts. The first part is the surrogate environment. We get this environment just based on the experimental data from the real, from the physical fish-like robot. Okay, and then the second part is just based on the communicational fluid CFD environment. We use a special software called HyperFlow from our colleague, and then we can get the exact solid and flow interaction. And then based on this framework, we can training the fish. First, we training in the surrogate environment, the speed very fast. And after some hospitals, we transferred to the CFD environment. Okay, here is we want to the target is to let the fish follow a geometric path accurately. This is the result. Okay, here is the trajectory, and the fish can finish the task efficiently. Okay, and similarly, we get the pose control. The pose control is more difficult than the trajectory following because they have 2 objects must be finished. First position, secondly the heading. We also use the same environment and for the training, and then it's get the result. Okay, and this paper has just published 2 years ago. Okay, and also we use this DR learning method with our artificial litter system. In this case, the task is a little simple. We just hope that attitude holding task for robotic fish swimming in unknown flow velocity environment. Okay. Also, this 3 step build the simulation environment, and then training, and then test it in the real tube. And here we use this equipment. We can control the speed of the water or the flow. And then here, when the water flow, the velocity of the water is changed, or flow is changed, the fish can sense the change of the flow, and then changing its control of the tail to keep the expect angle. Okay. And also, this paper just published last year in Trends of Robotics. Okay. This is the last thing is the international underwater robot competition, and now it's about 300 universities in China participate this event. All other so you are welcome to join this event. Okay. We have some of the fish-based water polo game, and also some for the garbage collection. So it is. So the event is very has a lot of types. Okay. Okay, that's the end of my talk. This video shows some of our robotic fish. Yeah, all these three kinds are developed in our lab. That's all. Thank you.
Thank you, Professor Xie. This is a fantastic talk. I wish you could hear an actual applaud. I'm sure people are applauding at home or in their offices around the world. We've learned so much about fish today, and we've had a wealth of questions pouring in during your talk. So hopefully you're okay staying for a couple of minutes to answer them. So I'm just going to go through them in sequence as they came in for your talk, and I'll summarize some of them. And if you have more talks, don't forget that if you have more questions out there, don't forget that you can post them both in Discord and on the Zoom chat channel. So the first question was about the sensor modalities of the fish. You already expanded on some of them, but people were asking, perhaps in relation to this morning's talks, about whether the fish also has haptics. So do the fish ever try to actually sense something by touching things?
Yeah, it's maybe, but in nowadays, we just focus on the literal system, just feel the water the information, because we just use the classical pressure sensor. We did not develop a new sensor to haptics. We cannot invent new sensors. So in the future, maybe, for example, in the CRISPR, we may integrate some haptic sensor to so that we can catch things more. How to say this? More have the feeling. Yeah, I think. Yeah.
With feedback control, yes, it makes sense. Thank you. So another question was, so regarding these lateral lines, which is, it's amazing that you implemented them, and fish depend so heavily on them. So the real lateral line, a lot of your work is on biomimetics, and the real lateral lines, they must have an additional mechanical function in them because there are these cilia hair inside, and then just a few openings out to the real world. And you've replaced that with pressure sensors. So do you think you're missing out on some of that embodied intelligence that happens, in the mechanical design of the lateral line? Is there more you can get?
Sorry.
Let me try to expand. So with the lateral line, right, there must be some probably mechanical filtering of the signals that happen, for where the sensors sit, which is inside the lateral line, a little cilia hair. And when you just have pressure sensors sitting on the outside of your robot body, right? You've already shown that you can use them for many different types of control. But I wonder if there's more you could get by, for example, implementing them on the inside of an actual lateral line instead, by making something that's slightly more biomimetic.
It's maybe yeah. You are right. I think if the chemical process is considered, the literal system may have more function than just the pressure sensor. Yeah.
Okay, I don't know. I'd be curious whether there was more you could gain from having that system on board your robot. A lot of people were interested in this idea of communication, electrical communication. So question number one was whether it was indeed biomimetic. Do fish actually communicate using their electrical senses, or do they only use it to sense their environment?
In fact, the weak electrical fish, it just in fact it's also called a lateral line system. For our research, it's just use the mechanical signal, but for the weakly electric fish, it's also called an electric lateral line system. They use the electrical signal to feeling the environment, feeling the food or his colleagues. For this kind of fish, the function of the air is almost lost. So we just use the electric lateral system to keeping his life. Yeah.
Interesting. So, okay, there's so much we can learn.
So we also developed. In fact, we also developed this new electric sensing system, and then we can locating the fish in a tank. For example, if you use camera, if the tank body is just a classic, you cannot see the body, the edge. But if we use this electric sensing system, you can think of, okay, we cannot go here, it's the obstacle. So we just develop this kind of research. So maybe this future we'll submit the paper to the journals. Yeah,
that's exciting. So we'll invite you back next year maybe and hear about this. So following up on those questions. So I think more from those who are interested in implementing this on their robots. Maybe there are questions about the bandwidth of that type of communication. How far can you communicate? I think you mentioned up to 10 meters. What kind of communication packets do you send?
From the theoretical analysis, maybe the 100 meters is the limitation, but I think in the future this kind of electric communication can just use between the robotic fish in a group. We just use it in the active when two fish want to exchange some information. If the fish, the robot can want to get some information from the land or from the fish or from the ship, we can use the traditional acoustic devices. Okay.
That makes sense. Okay.
Yeah.
Right. No, this is fascinating. And so another question was, a lot of this is biomimetic, but fish presumably don't try to communicate to, for example, do schooling or milling, right? Whereas you're implementing a little bit more of a traditional robotics approach where you say, okay, we communicate and we discuss exactly where to go, perhaps. So can you talk a little bit about the trade-offs between doing what the fish do and doing what what you do in robotics, what you choose to do?
Oh. This question, I didn't consider this question anymore. It's a good question, but in the future, maybe we'll consider this. Yeah, thank you.
Okay, fair enough. I mean, because there was sort of this the ad hoc networking is a very robotics-minded approach, whereas what the fish do presumably is a little more, I don't know, based on their gut feeling or the hydrodynamic flows around them or whatever they see. All right, cool. There were a few more questions, if you'll bear with us. Another question was about this idea that the robot can interact with the fish, and people are very fascinated by this. So are the fish actually perceiving the robot as a fish, or are they just thinking it's a robot and interested in it? And how can you make them more likely to perceive it as a fish, especially maybe if it has a tether?
This is a good question. We also show this phenomenon to the biologist. At first, we think that the fish think the robotic fish is the same, is the fish. But the biologist said that no, it's very complicated. We cannot get this answer directly. Maybe the fish just think here the flow, the rule of the flow is just let them can swim, use this, for example, energy harvest, because it can use the wave of the robotic fish generate. So the question is still open now. Yeah.
That's fantastic. That's very, very cool. I think on that note, this is a great opportunity. Thank you again so much for giving your talk. It was absolutely excellent.
The networking is not good. I cannot hear you.
Oh, I'm sorry. Let me check that I'm using the right speaker. I am. Okay. Well, what I'm trying to do is thank you very much for giving this fantastic talk, and thank you for answering all of our questions. And I'm sure everyone is applauding everywhere around the world. If you're interested, you're more than welcome to stick around for the panel discussion, and we would love to have you back at the discussion at the end of the day, although I'm guessing it's getting kind of late where you're at.
Okay.
Thank you so much.
Okay. Okay. See you later.
See you later.